This conference will now be recorded.
Okay, so there's always an internet connection to the World Wide Web, right? Through some type of internet gateway or point of presence, and this is generally connected directly to the central office or the head end, or sometimes hubs. And then there's always a connection to the long haul transport, so you can connect to the world outside of your metro area. So if we take a look at a closer look at what's happening in the carrier metro network, there's generally chances are a WDM connection going out to the network from the head end, but it doesn't have to be. And today there's various services that are tried on almost every market. So data center interconnect is a new, relatively new. It's been there for a long time, but now it's become large scale. So these data centers today are connecting with 100 gig WDM streams, so multiple channels on 100 gig. And really the interconnect is, back up from one data center to the other. And oftentimes it's out of the local network, out through the long haul transport to another data center. So this is redundancy normally to keep track, so that if something happens somewhere, they still have their data centers working. Somehow my controls are going crazy. Another big customer or service happening in the carrier network, as most people know, is cell backhaul. So cell backhaul today, it's 10 gig up to the towers. So the connection actually to the mobile switching center may be a lot more, and chances are it is, especially back to from the carrier network, sometimes back to the head end or the central office, but oftentimes just within the carrier network connected back to the MSC, the mobile switching center. And with 5G, we expect that this bandwidth will get higher and higher and higher, because 5G is going to end up offering a lot more internet service, a lot more services, a lot more bandwidth. So we can expect that to grow. Of course, business services between large scale headquarters are typically 100 gig today, sometimes 100, and 10 gig today, sometimes 100 gig, and even higher. But there's connections directly to the branch offices or through the carrier network to the internet, or out through the long haul to remote offices as well. And then there's residential distribution. So it's a business service in the sense that it can go to an MDU or control multiple customers through fiber to the home with PON networks, remote PHY, and dark fiber, and that kind of thing. So you have basically different networks that are connecting to the carrier network, all being managed by the central office. So this is the big picture. It's just to reiterate what's happening, and this maybe not even all inclusive, but this covers a lot of what's going on today. So if we take a look at a good example of talking about the different layers that people always talk about when we talk about testing. So layer 1, layer 2, layer 3, all the way up to layer 7. This Metro WDM network is a good example that lets us take a look at the different layers that are in play with these Metro networks. So there's been fiber rings around the big cities in this country for a long time. So Sonnet was there. Now these rings are being repurposed for high-speed internet, high-speed connections for customers, right? So if you take a look at the basics of how this operates, you have a layer 1 dense WDM network, which is the fiber, and there's optical add drop multiplexers. These could be just an optical add drop multiplexer. They could be ROADMs where you can reconfigure how the wavelengths are moving around, but it's a WDM type system. So you have multiple channels that are transported around the ring and can be out to the WDM transport, to the internet, or just making connections between customers. So if you take a look at an example of two businesses that are on the same ring, but on the other side of the metro network, oftentimes there's a switch handoff. So these optical add drop multiplexers can be passive or they can be active, right? So you could have transponders that take a 10 gig signal and transpond it onto a wavelength, a 10 gig wavelength. And then able to transport across the network. But anytime traffic has to use an address to be forwarded through a device, it's well, in this case, a layer 2 device, it would be Ethernet MAC address. You can identify whether it's a layer 2 connection or just a physical layer 1 connection just by that alone. So with layer 2 switches, it requires a MAC address, an Ethernet MAC address for any traffic to move. If we go one step further, the layer 3 type traffic uses a router. Today, routers and switches are interchangeable, it seems. So a router is not just layer 3, it could be layer 2 as well. And switches, there are layer 3 switches as well. So, but if it's using an IP address to forward the traffic, that's considered a layer 3 service. And all internet traffic is layer 3 service because it's IP based, right? And I want to mention something here. This network has a lot more to it than just this optical ring around the network. You still have a core MPLS possibility, a lot of different possibilities in the network. So this is a good example of the layers because there always seems to be a confusion. What does this layer traffic mean? Well, in layer 4 is the transport behind layer 2 and 3. Layer 2 slides into layer 3. It's the payload of layer 3 is a payload of layer 2. So there's more to it than what I'm saying here, but the big thing is don't worry about it. If you see IP address, if you need an IP address, you're probably going through a router. If you need the MAC address, you're probably going through a switch. You definitely are. Okay, get my mouse working correctly. So Metro Ethernet Forum, about 18, 20 years ago, decided to come up with standards for naming what was happening in the carrier Ethernet world. So there was already traffic going back and forth between customers, but then all the network equipment and all of the service providers were coming up with their own naming conventions and not classifying the service. They were all kind of proprietary. So what MEF did is come up with standard names for the services that are all going across these metro, and they become de facto standard today. So if we take a look at that, it's working. There we go. The most common service is the Ethernet private line, and what this was designed for originally was to replace DS3 or T1 or OC3 type services, where basically you're handing a bandwidth off or a bit rate transmission back and forth between, in this case, a university campus to a satellite campus. So this is just a good example to talk about it. So this is a point-to-point dedicated service, and it's really the most common service in the operator world today. And sometimes the naming convention will change. Oftentimes it's called E-line, and they're referring to all the different E-line services. Sometimes they'll use EPL or Ethernet private line. But this connection between these two handoffs, the uni handoffs, is not just a fiber loop, a fiber line. There's a lot of things going on in the background, and we'll talk more about that. If you're going point to multi-point, it's Ethernet virtual private line, where you would have one, in this case the university, have multiple VLANs terminating into it. So it's multi-point to point or point to multi-point. But the services are still dedicated, and there's configuration that has to happen in a network for this to occur. Another big, maybe becoming the biggest service is Ethernet Internet Access, sometimes called fiber internet service or dedicated internet service. Different carriers call it whatever they want to, but the idea is that it's a nailed up connection out through the head end or the central office out to the internet. So this is a common high-speed application for larger businesses, or in this case, the university. So what's important to realize, there's a lot of things that are happening in the background. This makes it look like you just run a piece of fiber from there to there and everything's working well. They're not dedicating the fiber to the customer, they're dedicating a service over the fiber. So how do they do that? Well, they use VLANs. They can classify the service, the priority of the traffic going over with class of service priorities within the VLANs, it could go through MPLS, or it could use other routing protocols to make this connection. So there's a lot of things going around in the background to make this happen. But this is a good high-level look at what it is. This is the service as defined by MEP, but actually in play by most carriers today. So this is what's going on in the background. There's a lot of switches and routers and different protocols happening. So what's important is you have to have proper end-to-end provisioning of all the network elements in the path in order to get this to meet the service level agreement. So the service level agreement says, hey, this is how the service is going to be delivered to me. And there's certain specifications that are agreed to between the service provider. Often it doesn't have to have a service level agreement, but oftentimes it does, especially with larger corporations, where you're agreeing to certain specs of how that network's going to behave. But if you think about it, there's a lot of pieces that have to be programmed exactly right. They have to be provisioned to pass the traffic from point A to point B, no matter what the configuration is, if it's the Ethernet private line, Ethernet virtual private line, or even the dedicated internet. You have to make sure that the MPLS core, if there is one, the edge routing, the aggregation from the high speed to the low speed, and then even the access, that everything is provisioned correctly. So VLAN tags and priority must be configured for all the switches and router ports in the path. If this doesn't work, nothing works. So this is actually when a lot of the calls that I get on with customers, it's something's provisioned incorrectly. So even if you're handing off a 10 gig service or 10 gig interface, a fiber interface that says 10 gig on the optics, it doesn't mean that the traffic is programmed to work at 10 gig. It could have rate limiting. And if that's wrong or done incorrectly, again, it's a provisioning issue. Also, if the path runs through the MPLS cloud, proper labeling and priority must be configured. So all the way through the network, through that cloud, it's not just that line, like I said, not just a fiber line, but provisioning of all the different pieces and parts that are making that circuit work. So this is important. This is an important thing to think about when it comes time to how do we validate this. So I'm going to switch gears a little bit. Just
real quick, Jamie, sorry to interrupt you. I'm having a little bit of trouble with your audio. It sounds a little tinny. I don't know if you're close enough to your mic or.
Okay, I can. Well, thank you.
Yeah, that's a little better. Thank you.
I sound perfect to me.
Yeah, I'm not.
So yeah,
it was good there first. It was good there for a second, but then kind of got tinny again.
Okay, are we good now? Are you pretty good now, or should I call in?
Go ahead and continue.
Okay.
There we go.
So, yeah, I'll stay this close. I tend to rock the back of my chair sometimes, so that's probably what's happening. So we'll take a quick look at 100 gig, because there's always the question, wow, 100 gig, now what do we do? Well, turns out 100 gig is very much like the lower rates as far as Ethernet's concerned. All the rules and all the rules of the standard of the protocol remain in place, but there is some differences, and that's what we're going to talk about here. So if we could do a comparison between 10 gig E and 100 gig E, it's pretty simple. 10 gig E uses a single laser with modulating the data with a 10 gigahertz clock, meaning 10 gigabits per second, right? So for every clock cycle, we get a bit out. So this is a single wave wavelength laser. It could be single mode. It could be multi-mode. Typically, most times, it is an LC connector today with SFP plus optics. And these optics can have different ratings. So with multi-mode, you're going to have lower or shorter distance, and then with single mode, you're going to have typical is 10 kilometers, but it could be 40 kilometers and it could be 80 kilometers. So there's different values as far as the optical power that's transmitted out of the SFP. And of course, the wavelengths vary too, depending on the distance. So 850 for 500, 1310 for 10 kilometers, and starts to get into 1550 for 40 kilometers and 80 kilometers. Also, the wavelengths could be tunable, or fixed. So you could have the wavelengths that are fixed to the ITU grid that would slide right into a passive WDM mux. So the output would have 15 dot whatever that number is for that particular channel on the ITU grid, or tunable. And this is becoming more and more popular now because the price of tunable optics has dropped. So this is the 10 gig, and a 1 gig is very similar, just 1 gig, right? And chances are 1 gig SFPs are not going to be long haul or longer distance. But if we take a look at 100 gig on the other hand, 100 gig utilizes or transmits 4 lasers modulating data at 25 gigahertz per wavelength per laser. So 4 times 25 is 100. And these can be single mode. It can also be multi-mode. With the single mode, it's a WDM signal. So 4 wavelengths are on a single fiber. If it's multi-mode, they're going to be multiple fibers, and you're going to use a different kind of transceiver called an MPO. So single mode LR4, long range 4, there's an ER4, there's different ratings for this stuff as well for distance. This QSFP28 seems to be the most popular style and form factor. So it's a little about the same size as XFP. There's a CFP4, which is a little bit bigger, but very small for 100 gig as well. And there's different frequencies that are being transmitted, or wavelengths that are being transmitted depending on the optics. So there's many types available with various wavelengths and distance specifications. So there's a CWDM version of 100 gig. The rules are pretty simple with this stuff. You want to connect the same transceiver that you're running under test, because you're trying to connect to some network gear and you want to match those up. So it's a very simple rule. Make sure you're using the same transceiver, unless you're going over dark fiber, and then you have to use the long haul. You're going to have to use a 1550 with long haul. So the typical single mode fibers, 4 wavelengths, and it has predefined wavelengths that by the QSFP standard. QSFP stands for quad, small form factor, pluggable, 28 gig. And then you said, well, why 28 gig? So I wrote up here 25 gig. I should have said 25/28. So 28 is for OTN. OTN's just the other protocol that adds some overhead to the Ethernet, and it's used primarily on the WDM systems. If it's multi-mode, on the other hand, you would have QSFP28, same thing, because it could still be OTN even though it's multi-mode. Multi-mode just can't go as far, and generally it could be less expensive. But the MPO connector is not a single fiber, it's 12 fibers with 4 transmit and 4 receive. So instead of having wavelengths, you have fibers coming out into a cable with a multiple fiber connection, or MPO, also sometimes called MTP. So this is the big difference between 100 gig and 10 gig, besides the rate, of course, but it's how the data is transmitted over these optics. So it's the optics. So this is a nice slide because it shows the actual optics that we just talked about. And it basically has 4 times 28 or 25, depending on what you're transmitting. Whether you're transmitting Ethernet, it would be 4 times 25 gig. 4 different lanes coming into the transceiver on the electrical side. All this stuff back here is happening in the network gear. And there's some things happening in the background. If you follow this from the Ethernet frames coming in, this is all round robin insertions. So these are 5 gig lanes on the electrical backplane, and the data comes in symbolized and walks through. So what this tells you is these 4 lanes, if it's Ethernet or OTN, they're not independent. They're all part of the same signal. So these are not like 4 different transmissions that we can split off and all that. It's really these four lanes are part of an Ethernet signal that's 100 gig. Okay, so back there you could multiplex and all that, but this is how it works. Or what is nothing to worry about. These 4 lanes are monitored. There's, by standard, there's a parity check going on, so you can see if there's any errors happening. But there is specifications on the timing on this. So why do we talk about it? Why do we even care? Well, we give you that information in our testers so you can identify, wow, maybe it's the transceiver that's the issue, or maybe it's the line card that's the issue. But so if we follow this through, we have 20 lanes coming in at 5 gigabit, and then we get 4 times 25, it's multiplexed. And then it comes into electrical optical converter where it's sending out, sending out optical signals into a optical mux. And this is one direction. There's obviously 4 channels going in the other direction too. So this is just to simplify. And then out the connector, the Larry Charlie connector, LC connector, we have the 4 wavelengths carrying out. So this is a good example. Again, this is a QSFP28 or a CFP port. This is the modern version of 100 gig today. So the optics, these optics have gone down in price, but they're still pretty pricey. So they're not your run-of-the-mill optics. Depending on the range, the lasers cost more. You got 4 lasers, and depending on the volume, these things could run anywhere from $2,000 to $10,000 today. So they're not. There's nothing that it's not something you can put in a shelf and say, well, I don't know if it's working or not. So we developed a test that you can plug into the tester and put a loop back on transmit to receive, and it will run this automatic test and scan it. And it's a pretty simple test. It can run for 30 minutes or 1 minute. So 1 minute to 30 minutes. And it kind of, when you put it in a tester, this application will know, it's called iOptics. It will know what's installed, and it will have a green check mark if you have a jumper on it. So you put a jumper on the transceiver itself. Say you suspect a transceiver failure in the network. You pull it out of the network here, put it in the tester, put a loop on it, run this test. And what it does is it reads the transceiver, in this case it was a Finisar, and it says, here's the power threshold for DC power or wattage. There's a temperature threshold, there's the transmit range, there's the receive range for optical power. Let's run a test pattern where we do full line rate data across transmit to receive and verify this thing works. And then we do a skew test. This is why I talked about the PCS lanes. This tells you that there's a timing spec that those lanes can't be out of time by this many bits, which is a certain amount of time. It doesn't matter. The tester just does it for you. And then when you run the test, this is an example of a test that passed. It does some communication to the pins on the back of the transceiver and makes sure that the transceiver responds correctly. Make sure that the commands back and forth to the optics are working. This is all automatic. There's nothing to do but just press go, and it takes about 2 minutes if you had it set on 1 minute. So 2 minute, 1 minute burn, 2 minute total test. So it does an IO check on the pins. And then about that same time, it starts measuring the power or the current and tells you what the current is. Then it looks at the transmit power coming out of the optical power coming out of the lasers, and then looks at the receiver. It will run some test traffic, bit test, a bit error test, make sure that none of the bits fail for whatever time you told it to. And the whole time it starts to measure the temperature, it keeps track of the temperature. So finally, it will do a skew test on 100 gig and tell you that the timing seems to be okay, that there's nothing going wrong. So you can tell that the optics isn't your issue or is your issue. And where we see these fail is right away, where they can't communicate, or we watch the power wattage go up and the temperature go up. Like most electronics, heat is the enemy. So these things, if you go back and look at the previous slide, you'd see that there's a plastic ejector handle. It's because they get pretty warm. So they run up to 70. This is rated at 70 degrees Celsius, right? But if you see the temperature rising up, you're going to suspect that maybe the optics is failing. But this is a good validation test to prove that actually the #1 failure in these networks is either a dirty connection or these optics. Okay, so moving on to carrier Ethernet testing, I kind of got off track a little bit with 100 gig, but it's important to see that and understand what that is. The rest of the tests that I'm talking about work for 100 gig, 10 gig, or 1 gig. So for carrier Ethernet testing, typically there's a service level agreement, and as I mentioned before, this is just a contract between the operator and their customer, specifying a certain amount of service level commitments. So here's an example. Committed information rate. This is the guaranteed bit rate or bandwidth of the service that you're providing. In this case, is an example for 1 gigabit. But this is an example. There could be more or less service level agreement parameters, but this is a typical one. So typically you're going to guarantee the traffic. In this case, they said you're going to, on a 1 gig, we're guaranteeing 970 megabytes bits per second, right? So we're guaranteed that rate. You could have a guarantee for the committed burst size. How big of a bytes can we take, kilobytes of burst can we take before we fail? So this is a possible service level agreement. I don't see it as often, but it's possible. Delay all the time. What is the delay? This becomes more and more important as these services, this 5G gets into the network more, and some time-sensitive applications like financial trades and stuff like that. So delay could be round trip or one way. Frame delay variation. So this is jitter, often called jitter, and it's basically inter-arrival time of the frames as they compared to when they left. So you don't want the frames moving in and out of time with each other. You want the time to stay pretty consistent so that you get good real-time traffic behavior, so voice and video and things like that. So jitter is important. Frame loss, this is just a guarantee, or what do you guarantee for the amount of frame loss that you expect to see? Because Ethernet, by design, is a best effort technology. So there's a lot of work in Ethernet. Most of the routing and switching and devices are there to counter the Ethernet's best effort protocol. So there is an acceptable amount of frame loss depending on the service. Mean time to repair, this is whatever the contractor agreed to, and then availability. So you've heard of 5 nines, this is 99.999%. So this is a typical service level agreement that's used in the business today. So what? Why does it matter? Or how do we validate it? So if you look at this table here, it does a pretty good job of letting you know what tests do we run to prove this out. So our availability Etherburst, which is basically a burn-in or a soak test. So you can run this as long as you want, and depending on the rate, it seems to be the higher the rate, the longer the test happens. At one time, everything was going for 24 hours, then it went to 10 hours, and now we're down to hours or even minutes. So availability on a BERT test is just, if it's built into the SLA, you'll probably end up running that test. Frame loss, we run RFC 2544 or the EtherSAN. These are both turn-up test examples, and we'll look at those in a little more detail. Frame delay or the latency, again, RFC 2544 or the EtherSAN, and now even EtherBERT has a latency test as well. So this is the test that you would use. Jitter or frame delay variation, the traffic generator and EtherSAN. Throughput, the same test. So you can see most of the tests are done with RFC 2544 or EtherSAN. For reliability, we have something called service disruption testing. So this is if you have protection switching guaranteed, so that you have a redundant path for the traffic. If something was to go, if a fiber was to be cut or whatever, we can measure the switch time and make sure that your reliability is correct. So taking a quick look at EtherSAN, it's an International Telecommunications Union, ITU, standard Y1564. We call it EtherSAN. Our guys were involved in this standard when they were produced. The idea of this was before EtherSAN came around or 1564 came around, Ethernet services was just a pipe, just another pipe. But nowadays, we see that there's multiple services running over the pipe. So in this case, we see a management with a certain guarantee, a video with a certain guarantee, and a voice. We know that there are different services running over cell backhaul. It's a good example as well. But triple play, right? And then a management maybe has a higher priority. So you could have 3 different services, 3 different rates that the services run at, guaranteed, And then you could even have a latency spec that's different for each service. So you could have a really high latency spec on management, because management kind of controls the billing and things like that. RFC 2544, this is a single stream service validation. So it's been around the block. It's been around for a long, long time. It was there to test the first Ethernet switches that were developed. So that tells you. But when Ethernet made it to the carrier business, there was nothing else, so they used this test, which is fine. But it is single service, and it's become more and more outdated, but you'll still have customers that ask for it. And it runs 4 different tests. Throughput, which is your bandwidth or your CIR. Back-to-back, which is a bursty test. This is usually not run in the carrier market because it requires you run at full line rate. In most of our, as I mentioned earlier, just because it's 10 gig doesn't mean that it's 10 gig service. So if you're running at full line rate, you're going to get errors when you're not really using the full possibility. So that's generally turned off. Then there's frame loss and latency. So these are the tests we looked at over here. Ethernet. This is like from the old legacy days of Sonnet and T1 and DS3 and all that, where you put a test pattern in your payload and you run it for so long and you look for no errors to occur, no bit errors. If you get all the bits back, you know that your service is working good. It also has the possibility of running service disruption time, which I talked about, and latency. So drilling just a little bit deeper, the Ethervert multiple patterns up to layer 4, which is the transport layer above layer 3, obviously. Integrated service disruption, silicon burn-in. Very straightforward, very easy test. It's a manual test. In other words, we could put a timer on it and run it for a certain amount of time. But if we press start, it will run until it's finished. And it will give you all the results in a logger file as well as in the alarm page. So it's a very, very useful test. As I said, it's generally done as a soak or burn-in test for high-valued circuits. ISAM, it's an intelligent version of EtherSAM, because what we did is we simplified the configuration to make it more common to what's happening in the world, where we run multiple services at the same time with different SLAs. We have the possibility of putting templates in there for SLA templates right into the tester, so there's nothing to do but just pick the template. So you could have a medium gold or platinum high or regular low, right, template as far as the specifications for latency, jitter, and all the measurements that it makes. So it gives you the possibility of storing templates, keeping it very simple, but also runs a layer 4 test, RFC 6349, which I just now talked about, right? Then this test is a TCP validation that is required mainly for internet service, but maybe some applications, some places would like that test to run. So this is ISAM. It's a one-page setup, sequentially validate the end-to-end TCP service using this 6349, and it has METH standard validation templates in there, as well as creating your own. So you can match your own SLA. So this is kind of a unique solution for Exfo. Very straightforward. And it actually manages the remote tester. In this case, you with RFC 6349, you would require 2 testers. EtherSAM, this has 2 phases. One is the configuration, or ramps the test up and make sure for each service that it can handle the CIR, and if you were doing police testing, you could test the policies to make sure that the traffic is doing what you expect it to do. So for each service, voice, video, or data, for example, you would run this 30-second test and tell whether or not the circuit's working, and then afterwards you would run all the tests with all the different services at the same time. So you would measure the performance on all of the services that you're trying to test at the same moment in time. And what's nice, I want to mention this now, what's nice with our testers is you can build configurations and you don't have to do this twice. Once you have it working, You save your configuration, you walk up, load up the configuration, maybe you have to change the address or something, but then it's easy to do. Of course, RFC 2544, single service or single stream, runs through these tests I spoke about earlier. It measures the throughput, the frame loss, and the latency of the network. So this has been around for a long time. For troubleshooting, this is a really nice test. It's easy to operate. It can be very, very complicated. You can do 16 streams, or you can do a single stream. And once people realize what this test does, this is usually the test that's started out before they try to turn up the circuit, because it tells them if everything's working right away. So you can see by this screen here, we measure the throughput, the jitter, the latency. We can run this to a loop, looping of other testers or other brands of testers, or to another test running the same application, either way. But we measure all of these parameters, jitter, latency, and frame loss out of sequence for as long as you want. You have total control. It allows you to do continuity of the circuit before you even start measuring. So you can do a ping across your 10 gig circuit or your 100 gig circuit. You can do a trace walk. You can make sure your VLANs are there. We talked about that. Make sure that all the VLANs are present in the circuit. You can troubleshoot bandwidth errors or CI error issues, latency and jitter issues, frame size issues or MTU size. All of the normal problems that we see happening, this guy is a really good solution for validating and troubleshooting that, finding the failure before you get stuck in a long process of trying to figure it out. So under the extra capabilities, it's the Pina Traceroute. We can do filtered capture. We can go into the 100 gig advanced and look at things that tell you that it's, hey, you know, this is the line card that we're connected to, or this is something came from far away, as well as the traffic scan, as I spoke about. So this is a very good troubleshooting tool, traffic channel monitoring. So if we look at this, the service turn-up connectivity, this could be a head-to-head with the E-line service, right? This is a typical way of doing it because you're not really going back to the head end or the central office. And if you have two Exfo devices, you can go bi-directional if you want, or you can do a loop back. If you have a third-party test or another brand, we can send a loop code to the other brand and run the test. And we run all of the normal turn-up tests that we just spoke about. So this is a maybe the most common test that's being done today, point-to-point service. In this case, I use the university and the satellite campuses as an example. The E-line internet access, this is a little bit more unique in that we're going to use different tests. So again, it's from the university out to the internet, through the carrier network out to the point of presence. We have rack mount solutions that are modular that you can put into different application blades or test modules. And you can set this LTV1, LTV2. You can install this in a secure location with remote access. So a lot of times these are in secure cages and it's hard to get in and out of them. So the ideal thing is to have this sitting on an adjacent port to the internet service and run the test from the test head out to the remote site. And you can do the bi-directional test, or you could do a loopback test. But the typical tests are going to be RFC 2544, 1564, and sometimes, depending on the service provider or the customer, you might have to do TCP testing too. But the TCP testing always requires two test sets. But this test set, the GUI, looks exactly the same as this test set here. So, and we can run this test to an Exfo or to another brand, or sometimes to a NID, depending on the NID. So this is a very common scenario nowadays, because especially nowadays with the sequestering that we're under right now with the virus. E-line testing, troubleshooting. Again, it's a traffic generator. We can test head-to-head. We can do a bidirectional. So this, we can run the traffic in 2 directions at the same time. If it's an Exfo, if it's another third-party tester, we can do a loopback, and we can do all the same tests. With the VLAN scan and the continuity, you don't even need another tester. You can just see, you can ping the address of the router. So we can just connect to one side and do those measurements. But if you want to verify and troubleshoot what's happening with the rate, the guaranteed committed information rate, the bandwidth service, you can you need another tester or a loopback. Isolate jitter and latency problems, MTU, and multi-service conditions, right? So you're able to test everything you need to troubleshoot the E-line services. These test topologies can be set up for inside out or outside in. So if you have an LTB2 located at your head end, or your central office, you can loop up or send bidirectional traffic to all of Exfo testers, no matter what network you're from our beginning carrier Ethernet slide, no matter what network you're actually connected to, you can test all the way back to the central office or the head end. You can use third-party devices and sometimes NIDs. So this is generating all the same tests that we just talked about, and also can be used for troubleshooting. So this is called inside out, from the central office out, but you can also do outside in. There's one advantage from outside in is that if you had a high-speed connection and your aggregation is switched to this test head, you could have a 100 gig port here and do multiple tests at the same time, looping the traffic back. So we have something called smart loopback that takes the incoming traffic, swaps the address, and sends it back out to the network. So, or where it came from, right? So we can loop back any one of these, and they can all loop up device as well. So this is kind of a maybe a little more efficient way of utilizing your resources, that you can have one device that's looping back multiple customers at the same time, so you don't have to wait to gain access to the testing. Just an idea. So obviously, Exfo testers could initiate a bidirectional test with the LTB2. So with that, we'll move on to the Exfo solutions. And we have a wide array of testers. If you're not familiar with Exfo, that's our whole business, is test and measurement and service assurance. So we are known primarily for our optical test solutions. Fiber inspection, turns out fiber dirty connections are the worst, or the highest probability of failure in a network is caused by dirty connections. So you have to have a best practice to inspect and clean. We hear often that, yeah, we clean the fiber, but that's kind of like, without inspecting, it's kind of like washing the window with Windex, but with blindfolds on. Same idea, right? So we have a really good solution that's very popular. Comes in different flavors. It can be USB, it can be Wi-Fi. Has analysis software that comes with it that helps you. So you take away the subjectivity of the is this clean or dirty, and this does it according to a standard, right? And we have a really good MPO tip that allows you to go through the multiple fibers efficiently and effectively. As well as, this is just a small sampling of all the different tips we have. We have all different tips that we developed for different angles and patch panels and all that. But the big thing is doing the inspection and having a tool that can look at the end face of the fiber. And then if you have the possibility of automatically centering it and focusing on it, and then taking a capture telling you if it's passed or failed according to specs. So there's something called Connector Max that comes with, that's available for your smartphone, for your PC, for any of our testers. The probe Wi-Fi, we run Wi-Fi because all the intelligence of the analyzing is done inside the probe, and the GUI is just to display the results.
So we have different standards depending on the type of optics you're using, and we have a standard for this core, the cladding, the contact area. We type it passed or failed. So we take away the subjectivity. And there's like a LED on the probe, so you don't even, if you had your phone in your pocket, all you have to do is look at the probe. If it's green, it's good. If it's red, it's no good. So this is a very, very popular and kind of an essential tool to have. Starting with the Max 800 series, this is the lower end. Nothing wrong with the quality. It's just it's a fixed non-modular platform with fixed applications. So we have different flavors of the Max. Max 860 is Ethernet only, up to 1 gig. Max 860G, that should say G, Ethernet only up to 10 gig. So we have Ethernet only. We have a Max 880 with Ethernet, OTN, and Sonic up to 10 gig. And we have a Max 890 Ethernet, OTN up to 100 gig. So we've limited the amount of applications you can have with this, and it's fixed rates. You're not going to be able to change out anything. It's just the way it comes as is. It's a very good tester. It works exactly in all the applications I showed you. You just have to have the right rate for what you're trying to test. So this is the Max series. We have a wide array of modular test platforms. So we have the FWB1 V2 or the FWB1 Pro. It's single or dual slot, so you can put one module or two modules into it. FWB2 Pro with 2 slots, and this has maybe more complicated OTN specifications and things like that. It's a little bigger unit, and also you can fit some of our 2-slot optical modules into it that work in here only. FWB4 Pro, which is a 4-slot module. This is what houses up to our 400 gig tester today, but it also handles all of the other modules that we have. And then there's the FWB500, which has 8 slots, and this will take care of legacy modules that we have. So we have modules that were designed, as well as modern modules that were designed some years ago that are still valid, and they fit into this platform as well. So these are modular platforms that are running Windows 10 operating system. They all have touch screens. They all have limited controls on the actual front of the chassis. You can see here on the FWB1, there's only a few buttons to press. The rest of it's all done in software. They all have the possibility of having a power meter or a red light source as an option onto the test platform as well. And here's the specifications for the CPU and for the operating system. This is common amongst all of the different chassis. So there's a quad 4 processor, Windows 10, as I mentioned. It's a wide open Windows platform. So it allows you to install whatever Windows application you find necessary, you can install on the tester and run it. It has a couple USB 2.0s, one 3.0. There's a micro SD memory card. There's a headset jack. We have an application that runs PRI. You have 128 gig memory inside of it, so it's not a slow machine at all. Most of the chassis run off of batteries. Some of them you're probably not going to carry it around with you. You're going to put it on a cart and put it in the central office or in the head end. But they're all field organized because we have a lot of optical modules. So this is the processing, the core processor in the specs for the PC. Looking at the LTB2, the rack test, this is the 2-slot rack mount. We also have an 8-slot LTB8, and any of the modules that fit into these platforms will fit into this. But primarily, it's for transport and datacom for the Ethernet and OTN and those type of applications for the LTB2. So it has multi-service test capability. You have remote operation. It's an open Windows system, so you could use remote desktop. You could actually install third-party access software if you like. It has a core processor, 16 gig of memory, a little more than the portables, and it's DC powered or AC powered, depending on what you like. The most common modules that we see going into this for the applications I spoke about are the 88200. Which is a open transceiver. We'll talk about this again in the next couple of slides, but this is a the multi-service module that can go from 100 gig down to 100 meg or 10 meg for that matter. It holds all the applications we spoke about. And then there's lower rate modules that can fit in here that can do T1 DS3, which as well as all the Ethernet and basic OTN. So this is the rack mounted unit, LTV2. We also have a wide array. This is just a couple of optical test modules that are popular. And these modules work in the LTV or in all of our platforms. The LTV8 can have the OSA. The LTV2 is primarily for the transport and datacom, as I mentioned. But the OTDR, it's the best OTDR in the business, and we have a wide range of these depending on your application. So metro or long haul or WDM or CWDM OTDRs. And ILM is Exfo design intelligent link mapping, optical link mapping, which makes the OTDR foolproof for the user that doesn't have a lot of experience. Optical spectrum analyzer, which we're, you know, in the head end or the central office, you're dealing with not only the transmission signals, the Ethernet and OTN, but also the wavelengths. So this gives you a chance to look at all the spectrum of all wavelengths in the metro environment, or even we have versions that are even the long haul with the coherent type signals. This is a look at some of the modules we have. 88-200, 100 meg to 100 gig. All transceiver based. There's no ports other than that. There is a timing port for latency and one-way latency and that kind of stuff. And then we have the multi-service module, the 8880 for 100 meg to 10 gig. The SFPs will support Ethernet, SONET, or OTN. And then we have also some physical ports for RJ485, T1, and DS3, and STS. Then we have an 8870, so we have a wide variety of these test plates depending on what your needs are. If you're never going to do any TDM type circuits, PRI, or any of that, maybe the 8880 works if it's all low rate up to 10 gig. So, and then the latest, and the one that I want to talk about a little more detail in the next slide, is the 88260. And it goes really from 10 meg to 100 gig Ethernet, as well as SONET, OTN, whatever application we can drive with the other modules, like the 88200, we can drive with this. So this is a new concept. We were seeing a huge change in the optics and the transceivers happening, so we developed a board, a module called the 88260 that includes an optical transceiver system where you have different test interfaces that slide in and out, test adapters that slide in and out of the system. So rather than redesign a whole new board, every time a new optics came out, we just designed a new transceiver system to plug in, a new transceiver adapter to plug into this. We call that the open transceiver system. So today we have one for synchronization. So this will run your sync-E and those type of tests that are happening more and more with the 5G. SFP28, which actually works from 10 gig, 1 gig, 25 gig. So this, now there's 25 gig transceivers that fit into this, and they're all the same size, they're all the SFP size. QSFP, we talked about this for the 100 gig. This is the slightly bigger. You can see it looks about the same size as the XFP, and this is your 100 gig. So dual SFP 28s, 10 gig, 25 gig. You could also add 1 gig if you wanted to, and fiber channel up to 32 gig. So it has dual port testing where all the tests that are listed here, where you can run the same test on either port. And then we have the dual QSFP28. So these are the ones, these are the most popular, and this is the standard kit that will come if you buy the 88260. So you'll get the possibility of a couple 100 gig ports and a couple 10 gig or lower ports as well. And then some fiber channel 25 gig as well. So this is the FTBX 88260, 10 meg, or actually 10 meg to 40 or 100 gig. And this works in all the platforms, all the modular platforms I showed you. So SB1, 2, 4, 500, and LTP. So there's a lot of applications, and they're really kind of module dependent. So if you don't have a port for T1, you can't do ISDN. But I wanted to make sure you saw all the applications that there are. So we have iOptics. I didn't speak about this very much, but this is a test, just briefly spoke about it, where it can test the 100 gig, but it can test any transceiver, where you put the jumper onto the transceiver, run the test. ISAM, I spoke about this, is the service activation and RFC 6349 test together. OTN, BERT, and then different varied levels of OTN depending on the module that's installed. You can do different tests, higher end mixed mappings and all kinds of things with OTN. But most cases, it's really just the OTN BERT. OTN is the signal that carries, that's being used by the density DEM to carry other signals. So it's often called the zero wrapper. So it's another protocol, and we do a BERT test. PRI, I mentioned, all of the Ethernet tests that we spoke about are here. Loopback, smart loopback, which you can loop back any traffic that comes to you. Just turn this on, and it will take the incoming IP address or MAC address or TCP port and send the traffic back to where it came from. We have a through mode, TCP throughput, carrier OEM, some synchronization testing, 1588, Sync E. We also do some wander testing. So these are all the applications that exist on the test platforms today. Okay, I got through in about the right time. So if there's any questions that I could try to answer, I'll be happy to. Can you hear me?
Yeah, Jamie, any folks that have any questions, I can unmute for the moment, and then, or if you want to jump in the chat box, looks like we got one coming in here. Thanks, Colin.
Okay. Sorry about the audio. I see that. I don't see any questions. I guess it was fine. Or if there are any questions, we're open. We're always open to help answer questions. If you have anything, feel free to reach out to me or Eric. We can go from there.
I'll stand by 1 second, Jamie.
Okay.
All right, looks like we're good. Yeah, like Jamie was saying, if you guys have any questions further on the 10 or 100 gig testing or testing for any matter, feel free to reach out to SLA Solutions or Exfo and get you in touch with the right person. But thanks everyone for attending today. I think it was a very informative presentation. Definitely probably opened up a lot of questions for folks. So I'll look forward to talking to you in the near future. So once again, thanks for attending, and we'll see you again next week. Next Wednesday will be actually at 10 a.m. And we'll be featuring the Fitel S124. It's a reschedule from a missed event. So thanks for joining, folks, and we'll see you next week.
Take care, everybody.